Exercise 11. And you might see this nice little scribble here. This is compliments of my 2-year-old son, Carter. He's getting very good at drawing random things. No, this is not a 9, nor is it a cursive J, like you would hope, because his last name is Johnson. This is, according to him, a circle with a line. And that's what we practice. So don't be confused by that. That's just Carter's drawing. He got a hold of my stuff and just started doodling, because he doesn't care about AP Chem. But you do. So let's get on to exercise 11. A white powder is analyzed and found to contain 43.64% phosphorus and 56.36% oxygen by mass. All right, so we're reading this problem and we're seeing that we're given percentages of different elements. Right? So this is probably going to be, just based on this, probably going to be a mass percent problem. Now, we're doing mass percent problems, so you already knew that, but I'm telling you, this is how you read the problem to deduce that it's a mass percent problem. Now, the compound, whatever this compound is, whatever this white powder is that has phosphorus and oxygen in it, has a molar mass of 283.88 grams per mole. So this is all the information we need. Blop, blop, and then the elements that they represent, and then the total molar mass. So we can just go to town. Now, on the last example, I showed you how to use the list function. I'm not going to do that on this one because there are only 2 elements. And to be perfectly honest, it's probably going to take longer to type in your list than it is to just set up your conversion factors. And plus, the only reason I wanted to show you the list function is so that when we get to kinetics, it's not as confusing, because we'll be using lists when we get there. All right, so in this substance, we have phosphorus. Okay? Now, how much phosphorus do we have? We have 43.64% phosphorus. What do I do with that? Well, I assume a 100-gram sample, because that allows me to transform these percentages into grams. And so I have 43.64 grams of phosphorus. And for oxygen, I have 56.36 grams of oxygen. Now I'm simply going to set up conversion factors, grams on the denominator so that they'll cancel. Moles will be on the top, right? Because I'm trying to convert into moles. That's moles of phosphorus. That's moles of oxygen. For every 1 mole of phosphorus, table. For every 1 mole of phosphorus, I have 30.97. Yeah, let's call it 30.97 grams of phosphorus. So we'll go with 30.97, and then oxygen. I remember off the top of my head, for every 1 mole, there's 16.00. If you put 15.99, it's not going to affect your overall value, right? So don't fret about that. And so let's do some calculations. Let's see here. Do phosphorus first. 43.64 divided by 30.97. Alright, so that's my first value. And then let's do oxygen. 56.36 divided by 16. There's my second value. Now I'm going to use what am I using? 4 significant figures here, so I'm going to go 1.409. Yep. And then to 4, that'd be 3.523. So that's the ratio of moles I have of phosphorus to oxygen. Now, I cannot write something as crazy as P 1.409, O 3.523. I have to get them to be whole number ratios. They have to be integers. And so remember, the trick I do is I pick whatever number is the smallest out of these 2, and I divide all of the values by that smaller number. So in this case, it's the 1.409. And this is obviously going to be 1. But what is this going to be? So let's take that value and let's divide it by that first value. Holy cow, that ends up being 2.5. 2.5. And so what I'm going to be tempted to write here is I have P1O 2.5. But I can't write 2.5 for my empirical formula. That doesn't work. It has to be whole. You can't have 0.5 of an oxygen atom. They have to be whole number ratios. And so what I'm going to do is I'm simply going to double, right, times 2, double all of those. So I'll have P2O5, right? So this is my empirical formula. It's the smallest whole number ratio of elements in a substance. Cool. So I have half of my question answered, right? Because it asks for empirical, but I haven't done the empirical formula yet. So I have empirical formula. And by the way, on the AP exam, if you're asked for an empirical and a molecular formula, just writing EF is going to be clear as day to the AP grader that this is the empirical formula, right? They know that you're being asked for empirical formula. So writing EF, they know that this is the empirical formula. Now, I've already been given the molar mass of the substance. So what I need to do is figure out the molar mass of the empirical formula so I can figure out how many empirical formula units it takes to get the molecular formula. So if you remember, I already looked at the periodic table to see what the mass of phosphorus is and what the mass of oxygen is. Now I have 2 phosphorus atoms, and so I'll type in the molar mass of phosphorus plus 5 oxygen atoms. I end up with a mass for the empirical formula of 141.94. And so for the empirical formula, P2O5, right there, the molar mass of this is P2O5. Sorry, is 141.94. But the molar mass of the substance is this. So I need to figure out the relationship between this and that. So I will simply type in that molar mass, 283.88, and divide by the molar mass of the empirical formula. I see that it's 2. Now, this is 2 examples in a row that have gone very, very smoothly and given me very, very round numbers. That's what you're going to see on the AP exam, right? You're not going to see something like 2.3 or something wacky and difficult. You're going to see something that, if you're using the correct procedure, the numbers will make sense. So I'm going to take that 2 that I just found out. I'm going to multiply each of these subscripts by the 2. So that means P4O10 is the molecular formula.